Hi, this is Elliot Fishman, and this series of talks is going to be on advanced cinematic rendering. And in part, this is some of the material we presented at RSNA 2020. I know, unfortunately, it was recorded, but you didn't see it in person, so you missed all of the excitement. So I thought I would share with you, in probably a two-parter, where cinematic rendering is today and where it's going. There's no doubt cinematic rendering, which is built on top of volume rendering, but the ability to do things differently, specifically lighting models, is because of the new GPUs provided by NVIDIA. And although the core technology in cinematic rendering has not changed in the last couple of years, I think you're going to see changes as we look to the next couple of years. But more importantly, the key is using cinematic rendering in practice, and I'll speak about that. Now, at RSNA, I would have said that RSNA 1985, 35 years earlier, Ed Catmull presented and his team about the Pixar image computer and how it was going to change imaging. It's amazing how many years have passed, which seems like only yesterday. And here's where the initial images, this is Lucasfilm's 1985, showing you that you could see bone, muscle, and fat. Now, of course, remember these are 4mm thick sections every 3 millimeters. Remember, this took 26 hours to render about 60 images. But it was a start. It showed the possibilities. And within a couple of years, we're able to get it down to about an hour a case. And you can see the quality of both the bone in this patient with a right acetabular fracture, as well as the muscle really showed you were going in the right direction. The original work, volume rendering, published in Computer Graphics in 1988, was done by 1985, though perfected over the years, focused on medical imaging. Three important names in computer graphics: Bob Drebin, Lauren Carpenter, Pat Hanrahan. If you look them up, Pat Hanrahan just won the Turing Award with Ed Catmull, which is basically the Nobel Prize in Computing, this past year. Lauren Carpenter is still doing his magic at Pixar, and Bob Drebin recently stepped down from Apple Computer. Three of the true geniuses of the computer age. Now, when we go back to what we published, volume rendering differs from surface rendering, which was what the only thing you could do at that point was, in that all information from the CT scans is preserved, not just boundaries. Object thickness and internal contours can be seen in the 3D projection. Now, fast forward almost 30 years, and now you see Crowe's was basically looking at volume rendering, but said, well, I have these new NVIDIA chips, and perhaps I can improve volume rendering by changing the lighting model. Instead of a single source lighting, perhaps I can have infinite sources of lighting. And you know that with cinematic rendering or any 3D rendering, the light source becomes critical. The better shadows you can do, the more realistic the images, and the better you can create the images. So that indeed becomes very, very important in how we do things. And I won't go into this technique that he used. It's a good article worth reading. It's a Monte Carlo integration. But you can see that he was able to create really high quality images. And his combination of all the work he did, in addition to the fact that photorealistic volume renderings tend to be aesthetically more pleasing, it has been shown that realistic lighting contributes to 3D understanding and can improve depth-related task performance. With this work and the implementation that we have made available, we hope to contribute to the uptake of realistic illumination in interactive direct volume rendering applications. And indeed, Crowe's did an amazing thing. Now, cinematic rendering is still not mainstream. But the truth is, I've always been disappointed about how hard it's been to make 3D imaging mainstream. It's still done in less than 10% of practices. There's been some uptick with cinematic rendering, but cinematic rendering has been around for 4 years. And as of October, there were only 86 articles. And as of today, when I'm recording this, which is January 2nd, 2021, there are only 88 articles. I think we've been slacking at Hopkins. We need to publish some more articles. But you can see that the importance of volume rendering is not lost on our surgeons or referring clinicians, but it's just been sort of something that's kind of not really taken off for whatever reason. And in fact, when you look at the 86 articles, or 88 now, many of these are case reports which show one image, or it's an article that shows one image, and they use the word cinematic rendering to make the articles seem cool. But again, our referring clinicians, our surgeons want to use cinematic rendering for preoperative planning, be it pancreas, kidney, liver, or vascular imaging. And in the refresher course that we were going to talk about, we were going to look at some of the directions cinematic rendering was going. And again, I regret I was doing an advanced course with Linda Chu. I was doing a basic course with Linda Chu and Steve Rowe. Hopefully RSNA 21, but surely RSNA 22, if they invite us back, we will show you some amazing stuff. But let's look at where we stand. Based on the literature and our own experience, areas where cinematic rendering has been successfully applied has been oncology, surgery, particularly cardiac and GI surgery and plastic surgery, trauma, in neuro, and in vascular imaging and vascular surgery. The common ground for applications tends to be complex anatomy that's best viewed in 3D, and then cinematic rendering makes this visualization even better. The more complex the surgery, the more difficult the surgery. Also, the use of laparoscopic surgery or robotic surgery really makes this super important. Where cinematic rendering is going and the need for advanced imaging, I think, is very clear. The question is, how is it going to happen? The challenge, I think, really relates to many things. Our practices now are RVU based. Everyone is worried about how many RVUs you generate. If you don't get paid for it, you're not going to do it. 3D has never been well reimbursed, or now it gets built into the code. So whether you do 3D or not, you're getting paid the same amount of money. I know we're not all about the money, but in practice, with many groups measuring how many RVUs you do, radiologists are not willing to do things that give them 0 RVUs or take lots of time. It's much easier to read a non-contrast chest or read a stone protocol and get your RVUs. So some of the challenges for cinematic rendering are not unique to cinematic rendering. There's need for a billing code with satisfactory reimbursement. We need better guidelines to when the techniques should and should not be used. And then, of course, there's variability in image quality. People can make all sorts of images. I see 3D imaging sometimes. I rather look at the axials. So it's really the quality that becomes critical. And then, of course, the clarity. Is this a 3D lab? Is this a technologist? Or is this a radiologist interactively doing it? Of course, we've always been the proponent of the radiologist doing it. I know many places have 3D labs, and many technologists are well versed in doing it. But I think as a radiologist, you know the questions you need to answer. When I do a 3D of the pancreas, I know to show the celiac and the SMA and the portal vein and the SMV, and I know to show the relationships that the surgeon is going to ask me about in conference. By knowing what the referring clinician needs, you as a radiologist are the best ones to do the 3D imaging. Now again, I'm not saying 3D labs are bad. I think the key for cinematic rendering, as with any 3D, is the use of presets. I have about 150 presets that take me about 90% of the way to 95% on all cases. Then I can adjust from there. That speeds up the process. I could do any case with filming in under 5 minutes. So really, it's not that long a process. Now, it does take expertise, and it does take those presets, but it is something you can look at. Now, again, this idea about RVUs, but the ACR is pushing for quality over quantity. That's a great start, and perhaps they should focus on 3D imaging. Changing, of course, this RVU-based process is going to take time. Cinematic rendering, like all techniques, needs a champion in your practice. If one person really wants to do it and gets good at it and pushes it, it'll work. If no one's interested, think virtual colonoscopy, then you're not going to be doing them in your practice. And this has been a challenge with many things, from cardiac to virtual colonoscopy to 3D imaging. You really need someone who really wants to do it, Now, the optimal workflow for cinematic rendering would be if the optimal preset or a series of presets could be created by the computer. And we've looked at this briefly, but the use of AI, if they look at the 2,000 or 3,000 pancreatic cancers I've done, and I've saved the cinematic rendering, and then calculate what the best parameters are for the next case. That would indeed be exciting. If I was able to simply sit down, open the case, and there were 3 to 5 presets that I could simply use for the vessels, for the tumor, for the gland, and I didn't have to do anything myself, that would be ideal. Now, of course, there are challenges. There's variations of the images based on patient size and contrast delivery. But again, with AI doing everything else, this might be an optimal opportunity to integrate AI. Now, the range of visualizations in any one case will need to vary, of course, right? Because if you simply look at this case, this is a patient with IV drug abuse and a groin infection. But you could see as I change the renderings, you go from the skin down to the adenopathy in both inguinal regions. I show you the muscle, I show you the vessels, there's no pseudoaneurysm, and I show you the bone. So simply having one preset may not be perfect, but again, the ability to come close to the optimal preset and then letting you adjust things as I'm adjusting them here on the fly becomes a very critical way of doing things. And I think it becomes very, very important. And again, this idea of being able to visualize and change things on the fly becomes very critical. And you can see why it's ideal for me as the radiologist to review the images interactively rather than having just a few snapshots of what I need to see. Because now I'm very confident the vessels look good, there's no pseudoaneurysms, which often happen in patients with IV drug abuse, and I can tell precisely what's going on. This idea about AI and deep learning, we are doing this on pancreatic cancer detection. If you can detect 1 centimeter pancreatic cancers that radiologists miss, it seems to me this best fit idea is an excellent idea. And again, the presets can transform the data into what the radiologist could then look at. Now, it's not a new concept. Back in the late 80s, early 90s, we tried to do this with Pixar because it took so long to create an image. And if you created the wrong preset, the image would have been of no value and you would then have to spend another hour or two redoing it. We wanted the computer to quickly create 4 to 10 potential visualizations, and then you, the radiologist, would pick the one you like best, and then the computer would render the entire data set. Unfortunately, Pixar got out of the computer business, and so that idea was never done to its fullest. Now, if you ask me about trapezoid creation, I've created the trapezoids. It's not easy because I really don't understand the curves. They don't seem to work as well as you think they do from a mathematical performance, but when you play around with them a lot, you can make really good presets. And presets are the key. And you can see on this picture here, you see presets for sinuses and pancreas vessels and liver. The truth is, for the pancreas, I have about 15 presets, from the vessels to the pancreas to the gland to all sorts of things, including the liver. So you're going to need a lot of presets, but again, you could do that fairly quickly. And again, you could just see a look of the presets I have. Again, there is variation, patient size, contrast delivery, all sorts of things. But I think you can use the presets to bring you pretty close. As I mentioned, AI would be ideal. And we started this on pancreas, but unfortunately the person who I was working with had to go back to China, so we really haven't done it. But I think it's something that you are going to see happen in the near term in the future. Now let's look at clinical examples, and the rest of this talk for the most part is going to show you where we are and where we think we're going. With pancreatic tumors, it can optimize lesion detection, particularly small tumors. The texture mapping can help you not only detect tumors, but determine lesion type, from cyst to spen. And again, how good it is a great question. Vascular mapping, of course, arterial and venous, helps determine resectability. And the pre-op plan, particularly with laparoscopic surgery, becomes important. Here's a nice example of a 1 centimeter neuroendocrine tumor tail of pancreas. You see it on the axial views. You see it nicely on the 3D rendering. And you can see as I change the texture maps, you can really accentuate the lesion very nicely here. You can see it better here than here. And one of the things you realize, and one of the challenges with cinematic rendering, of course, as with any 3D, you could hide things as well as show things, which is why the optimal visualization really becomes the key factor. Another patient, neuroendocrine tumor, calcification centrally. This is an unusual neuroendocrine tumor in the sense that it's not as vascular as many. There it is nicely on the MIP imaging. You see the coarse calcifications. You could have thought of a serous cyst adenoma based only on the calcifications, but the lesion is enhancing. And here you see it very nicely on the cinematic rendering with the textural changes compared to the gland, compared to the spleen, compared to the liver. Another case of a subtle lesion which was initially missed. There it is in the axial view and on the coronal view. But look how much easier it is to see. Imagine if the computer gave you this volume display, and there's the 1 centimeter lesion in the tail of the pancreas. Again, you can see this rendering is different from the one I used previously. It kind of makes the pancreas show the lobulations better texture mapping, and a better visualization. Here's another pancreatic case. Here the patient has a subtle mass in the head of the pancreas. You can see it on the axial and on the coronal, but you see the textural change on the cinematic. You see it here on the coronal as well. So again, one of the things I've been looking at and thinking about is using cinematic rendering as a way of enhancing the textural changes and enhancing detection of small tumors. I think that with AI, that's one of the things that AI in fact does. It looks at the texture and then tries to figure out changes in texture. Now let's look at a second topic, liver tumors. What do we do with cinematic rendering? Well, the goal would be to optimize lesion detection, optimize texture mapping to determine the lesion type based on enhancement patterns, vascular mapping of both the arterial and venous structures to help with planned resection. And then again, this whole idea of preoperative planning, looking at the tumor, adjacent organs, as well as vascular map. Here's a nice case. Surely you see it well. This almost looks like a pseudocapsule hypervascular lesion in a non-cirrhotic liver. There's the neovascularity on the MIP imaging. But look how nicely you see it on the cinematic, arterial, and the cinematic venous with the pseudocapsule. So I don't think we're going to reach the point where we don't use MIP. I think you're going to use the MIP and maybe standard volume rendering at times with the cinematic. So again, it's a composite, and you can see when I put everything together, it's just a beautiful group of images that helps the surgeon determine what they're going to do. Another patient, here's a smaller hepatoma, 2 centimeters or so, in a cirrhotic liver. You can see the perfusion changes nearby. And look how nicely the lesion stands out with the neovascularity on the patient's cinematic rendering, and there it is as it washes out on the venous phase imaging. And here's another example of a hepatoma, which invades directly into the main and involves the left portal vein. Again, you change the rendering parameters to be able to optimize the visualization of the portal vein, the tumor, and the invasion. Very nicely shown. Now, there are a number of other things we can look at, including small bowel. But I think let's take a break, let's get a cup of coffee, and we'll come back in 5 minutes and start again.
If you liked what you heard here today, please make sure to hit that subscribe button and visit our website, CTisus.com, for lectures, quizzes, pearls, and more. Also, be sure to check out our apps that are available for free on the Apple Store. All links are in the description box below.